We begin the third lecture of the course time series analysis. The topic of today's lecture is more practical. How to specifically predict the series using autoregressive moving average models. To begin with, we start by learning how to calculate forecasts using formulas. This is a little routine, but nevertheless, a student, a specialist in the field of time series, should understand how it works if it is all programmed by hands using specific formulas. So here will be a math. Any forecast is built in such a way as to minimize the error, given the available information. If we minimize the square of the error, here we have yt plus h. This is the actual unknown value of the predicted indicator for h period ahead. But this it plus h with a cap, this is the forecast obtained from the model for h steps ahead. This is the square of the deviation from the forecast provided for some information that is available at time t, including estimation methods used. If we minimize the expectation of this error, then by property of the function of the minimum of the squared error, the estimate corresponds to the average forecast or the mathematical expectation of the forecast. For the autoregressive model, this means that our optimal forecast, which gives the minimum squared error, is the expectation of the future value y on h steps ahead, given the available information ft. In essence, this will simply be the formula of the autoregressive process. The autoregression coefficients, the sum up to the order p, and the actual values or previous predicted values with a lag. That is, if we make a forecast one step ahead, the previous values are taken. If a forecast is made for 2 steps ahead, the forecast one step ahead plus the last known value is used as factors. And of course, plus a constant, a0. Now let's talk about forecasting error. This is the forecasting error that we need in order to calculate interval forecast. So usually we need not only the average or central forecast, which is calculated simply by this formula, but in order to calculate the boundaries, we need some possible spreads given by the confidence interval. Forecast error is the deviation of the actual possible value from the predicted value. And this will be our actual value, which is generated by the autoregressive model with the given parameters, plus the error per step ahead, minus the average forecast by the autoregressive model. The error has a normal distribution with some variance, respectively. If we transform this, combine the first term and the fourth term, then we've got the bracketing of the autoregressive parameter. Here we have a prediction error for h step ahead. This will be the autoregression parameter multiplied by the lagged error and plus the error of the current forecast. Well, since the model error itself has a normal distribution for h step ahead, the forecast error also has a normal distribution in this case, because it turns out that this is the sum of normally distributed random variables. For one step ahead, forecast error according to this formula will simply be the error of our model, since the previous values are fixed and cancelled in this formula. For forecast 2 steps ahead, the forecast error will already be the current error 2 steps ahead plus autoregression on the previous error, and so on. Now we can calculate the variance of the forecasting error. We really need it in the future. To calculate the variance of the forecasting error, we apply the variance operator to the left and to the right part of this formula. That is, here we've got I squared multiply the error variance plus error variance. We take out the error variance, it remains 1 plus I squared. In general case, if we apply the variance operator to this formula, then we've got the following equation. The error variance for h step ahead is 1 plus the sum, the counter from 1 to the minimum value between h minus 1 and p. H here is a predictable period, and the p is the order of autoregression, multiplied by the autoregression coefficient I squared, and after the bracket, already multiplied by the variance squared. Now let's consider the formation of a forecast using a moving average model. Similarly, as in the autoregressive model, the optimal forecast corresponds to the expected value. And for the moving average process, this means that the optimal or average forecast is the moving average model itself. The sum of the coefficient from 1 to k, the coefficients of moving average model, by, multiply the expected error with a lag. The forecast for h step ahead, respectively, is the error with a lag t plus h minus e, where I corresponds to the lag, plus b0. Historical errors that have already materialized are taken as actual ones, and new errors are taken according to the expectations. And here we actually have a mathematical expectations equal to 0. If b0 exists, then the error expectation is 0. Accordingly, the forecast error is also calculated as the actual value according to the moving average model. Here it is the actual value taking into account the error minus this optimal forecast. The same thing, we combine the first and the third term, put b out of brackets, and now we've got that the corresponding forecast error for h step ahead is the coefficient of the moving average model multiplied by the deviation of the current error with lag e from its expectation and plus and the initial error. Since the deviation of the error from the expectation of the error is 0, this will simply be a lagged error. Accordingly, for a forecast 1 step ahead, the forecast error will be simply the error itself, that is epsilon t plus 1. For a 2 step forward ahead forecast, the forecast error is exactly the same as the coefficient of the moving average model, multiply the previous error plus the current error. Well, accordingly, we apply the variance operator to the left and the right part, and it turns out that the variance of the forecast error is 1 plus the sum of the coefficients of the moving average model squared. The sum is calculated to a minimum, that is either to h minus 1 if we forecast not far, or if we predict far, then to k, and multiply all these by the error variance. Now the formula for ARMA forecast. According to ARMA model, everything is the same. The average prediction or optimal prediction is calculated simply by plugging the previous y values or the expected errors into the ARMA model itself. So these are our ARMA model autoregression coefficients. These are our ARMA moving average coefficients. This is our constant. In fact, this is a combination of AR and ARMA models. The forecast error is also calculated through the substitution of the actual values with an error minus the predicted values without an error. And we will have the sum up to P of the autoregression coefficient for the deviation of the actual Y from the predicted ones, plus the sum of the coefficient B of the deviation of the actual errors from their expected value. The expected value is 0. And plus the current error. Also, this prediction error has a normal distribution because the original error values have a normal distribution. So we should calculate the forecast step by step. Here it is shown that the error for ARMA one step ahead is just the error of the model. And the forecast error 2 steps ahead is already A1 plus B1 multiply for the T plus 1 error plus T plus 2 error and so on. It is no longer possible to apply dispersion with such a model. It is impossible to calculate the dispersion operator analytically because we have a dispersion condition for the sum of correlated values there. And it is already so easy not to calculate it all. Therefore, the variance of the predictive error for the ARMA process in programs is calculated through the representation of the ARMA process in the form of moving average with infinity. And then, according to this variance of the predictive error is calculated according to the formula of MA with infinity. Only we've got that sum BA with dash coefficients, which obtained as a result of the representation of the ARMA model in the form of MA with infinity. But this is how it is considered in the programs, and manually it is, of course, a little inconvenient to calculate. To calculate this manually, you need to take separately not only ARMA PK, but also make MA with the maximum possible number of legs. The number of legs here should correspond to the number of initial data. If we take the maximum, for example, and in this case, evaluate the parameters according to the moving average model and calculate the error variance according to the moving average model, and then this will give some error to put it here. Let's look at the application of these forecasting methods in the following example. We need to construct a forecast of the inflation for the United States using an autoregressive model. In the previous lecture, we have already estimated the parameters of the autoregressive model for this time series. This was autoregression model 4. Here it is presented on the slide. Here is the standard deviation of the error of this model. At step 2, we calculate the average optimal inflation forecast Y cap with T plus H and calculate the variance of the forecast error using the formulas on the previous slide. So the average optimal forecast is just a substitution of the actual values. Then, when actual values run out, we substitute the predicted values instead of the actual ones, and so on. By recursion, we've got a forecast for any number of steps ahead. Also, the variance of the forecast error we calculate through the epsilon variance and through the autoregression coefficients according to the formula. At the step 3, we use the error variance to calculate the upper and lower forecast. That is, we have the property that the forecast error has a normal distribution because it is formed as a result of the sum of normal values. And for normal distribution, we know that the boundaries of the normal distribution, upper and lower quantiles, are the central value of the distribution. Here is the optimal forecast, the expectation of the forecast, plus minus, plus in the case of upper forecast, minus in the case of lower forecast, standard normal distribution with a given probability alpha, where alpha controls the required quantile of the distribution, the required confidence level. For example, you can set 0.95 as alpha, then there will be a 95% bound, and multiply by the root of the error variance, which is the standard thing for normal distribution. Here, these predictions presented in the chart. The black line is the actual inflation data. The orange line is the average forecast. The red line is the low forecast. The green line is the high forecast. Here is the same thing, only enlarged so that the scale is more visible. Now this blue twitchy line is step 4, the so-called simulation forecast. It is also necessary. A simulation forecast is one in a million or billion set of possible simulations of a random variable. This simulation prediction is widely used in complex system modeling, where you cannot calculate the prediction directly from formulas. Such models, such systems quite often arise when you model a real system. There, such properties of systems are obtained that there are no standard analytical formulas for calculating the forecast. In this case, the main way to calculate the forecast is a forecast based on simulation. The simulation forecast is calculated as follows. For each steep ahead, simulation forecast will be an autoregressive model with reference to previous values plus the current period error. The simulation forecast is calculated recursively. The autoregressive model one step ahead relies entirely on known y. So for one step ahead, h equals to 1. These first two terms are constant. Lose an error for the first period. For the second period, the forecast refers to the already obtained forecast values for the first period, the values obtained taking into account the error that fell in the first period, plus the constant values that were in historical period, plus the error for the second period, and so on. For the third period, the simulation forecast is based on the parameters of the autoregressive model plus the error for the first period, the second period plus the error of the third period, and so on. The simulated prediction, blue line, will twitch every time because it is recalculated. That is, it is not a constant value. It can be seen that it falls within the specified 90% confidence interval with a 5% quantile, respectively. The probability of falling between the red and green line is 90%. So what is important to pay attention to? Here we construct models on the first differences for the price level. That is, United States inflation is the first difference of the price level. And here we have these formulas for the initial indicator on which we build the model. In this case, the model was on the first differences. Respectively, these formulas are for the period of the first differences. But what if we need to get a forecast of a higher order indicator? That is, if we have the first differences, this is inflation, respectively, and indicator of a higher order is the price level. We take the first differences from the price level and we get an inflation. If we simply apply the properties of log return and try to raise this forecast to an exponent and multiply by some initial value of the price level, then this formula will not work. If we take the price level, the forecast for each step ahead, the upper and lower forecast, it will not be equal to the last price level that we knew, multiplying the exponent of the sum of the upper and lower forecast of the first difference. This formula will not work. If we try to perform the same operation for the average value, then it will work. But for the upper and lower forecast is no. Let's see how this will actually work. How to construct price level forecasts based on the forecast of the first differences. The average forecast of the logarithm of the price level, it must be noted that we have logarithmic differences here. So it will be the logarithm of the price level, corresponds to the sum of the logarithm. The logarithm of the price level forecast is the logarithm of the price level forecast for the previous period plus the average y forecast for each step ahead. So for average forecast, this formula works. For simulation forecasts, this formula also works. It is the logarithm of the price level h step ahead with the logarithm of the price level h minus 1 step ahead plus the average forecast plus the error generated at time h. It is clear that the simulation forecast is again obtained by recursion. First, we make a forecast for one step ahead based on the historical values of price level. Then for two steps based on the price forecast for one step ahead. Then for three steps based on the forecast for two steps ahead, and so on. But the upper and lower forecasts are not considered according to this formula. Some modification is needed. The slide shows the modification of the formula. These are the correct formulas for calculating the upper and lower price level forecasts. The upper and lower bounds of the logarithm price level for each steps ahead. This is the average value of the forecast of the logarithmic price level plus minus normal standard distribution with alpha parameter multiplied by the root of the variance of the logarithm of the price level, not inflation, but the price level on each steps ahead. If we build the forecast for one period, then h equals to 1. If for two periods, then h equals 2, and so on. In this case, the variance of the logarithm of price level is calculated using the following formula. The variance of the logarithm of the price level, that is the original series, is the previous variance of the original series plus the variance of the residuals of the first difference model for the current period plus 2 multiply the sum of the lag covariance of the first difference from 1 to the minimum of h minus 1 and p. In this case, the initial variance of the logarithm of the price level, that is p small with index t, equals to 0 because we know the original last historical values. This formula is derived from applying the variance operator to the sum of the first difference and the previous initial series. The figures below show the forecast of the logarithm of the price level for the model. That is the same inflation forecast as at previous slide. Only this is the forecast of the series of a higher level, the price level. This is the logarithm of the price level. This is the average forecast, the orange line. The red line is the lower forecast. The green line is the upper forecast. The blue line is the simulation forecast. This graph is the same, only larger. And the simulation forecast is slightly different because this is another simulation. Accordingly, when you need to predict not the logarithm but already the original indicator, you just need to take the exponent from all four forecasts of the logarithm, upper, lower, average, and simulation. And then you've got the forecast of the original series. Not the forecast of the logarithm of the price level already, but simply forecast of the price level. In your handout, there is a file called US Inflation Forecast. And it has an example of this inflation forecast calculation that I just showed you on the slides. Here we have an ARMA model that has been estimated in RStudio. Here is this model. The coefficients are simply put in here. Here we have a column, the logarithm of the price level. Here is US inflation. This is the first difference of the price level that we predict. And here the IR4 autoregressive model introduced through the Excel function sum product. This is the product of the autoregression parameters, the fourth coefficients, multiply on the inflation with leg 4, the third coefficient multiply on the inflation with leg 3, the second multiply by leg 2, the first multiply by leg 1, and A0 is the drift coefficient. And here is the IR4 model. Then the average forecast, this is the forecast period, forecasting data. The average forecast is calculated by the usual autoregressive model, the error variance, and the upper and lower forecast, and the simulation forecast for the first differences. And here in orange columns, the error variance, the average, the upper, the lower, and the simulation forecast for the price level are calculated. So other sheets show subtleties. The IR4 Excel sheet shows how we evaluate parameters in Excel by minimizing the sum of square differences. I will talk about parameters evaluation in Excel later. Other sheets are the finer points of parameters estimation and forecasting by moving average, ARMA, comparison of AR, MA, and ARMA models. That's what we were going to talk about on this slide now. Let's continue. Here, based on the results of the US inflation forecast file, a comparison of the first differences in the forecast between AR, MA, and ARMA models is presented. I already said in the previous lecture that these are very closely related models. They are representations of each other. Naturally, we can observe in the US inflation forecast that we built in this example a close relationship between these three forecasts. The orange line is the forecast for ARMA model. The blue line is forecast for IR model, and the red line is forecast for moving average model. It can be seen that they give almost the same thing, while ARMA is some kind of averaging between IR and MA models. Further, after a certain level of lags, the forecast for all three models practically converges. All the difference is only in the subtleties that are first three steps ahead. If we look at the average price level forecast, these accumulated effects associated with initial differences lead to the fact that the price level forecasts differ in the long run. For example, due to the fact that the autoregressions shows a high inflation rate at the very beginning, we've got the price level according to the autoregression model to go slightly higher than according to the moving average and ARMA models. Well, I have no evidence that any of the models systematically outperforms the other in out-of-sample prediction evaluation. I tend to use either the autoregressive model or the ARMA model because it is always compromise between the two models and ultimately the model that uses the fewest number of parameters. Again, if you compare the error in the predictions between the three models, if you compare it with the possible error variance, you will see that the error variance is much larger than the deviations between the three forecasts. So it doesn't really matter which model you use to predict. Probably it is better all the same with a model that has a minimum number of parameters. Once again, these three models are almost identical. Well, this graph shows the upper and lower forecasts, which are calculated by the formulas. Everything is the same here. Almost the same patterns, they are repeated. And here on this chart, we have the upper, lower forecast for all three models for the price level indicator. There are also small differences. It is difficult to say how critical they are in an out-of-sample assessment of the forecast accuracy. I have no unambiguous answers. In my opinion, these are approximately the same forecasts which, due to some unpredictable accuracy, give certain errors. Here we talked about the fact that it is impossible to calculate the error variance using the ARMA model. For this, the representation of the ARMA model in the form of moving average model with infinity is used. We ourselves cannot calculate this representation in Excel, so on the previous slide I calculated the forecast for the ARMA model based on the error variance for the moving average for thin model, which I already estimate in the US inflation forecast file for the EMA model. In fact, the lack of an accurate estimate of the error variance for the ARMA model necessitates the use of simulation to obtain an interval forecast from the ARMA model. And in many other problems, this simulation becomes useful. In essence, it is a way to get an interval forecast for some complex system for which we do not have analytical formulas for calculating the interval forecast. So let's take a look at the steps of this simulation on this slide, its main stages. Let's start from the first step. First, we need to build a simulation forecast of our indicator. On the previous slides, we have already built a simulation forecast. This is the model itself plus the error. For example, in Excel, every time when you recalculate cells, pressing the F9 button, or when you make some changes to empty cells, then this simulation forecast should change, because every time it is based on the random number generation, R&D function in Excel, or some other random number generations function in other application packages. At step 2, we need to make from 100 to 10,000 forecast simulations. We have to write down the simulated forecast series somewhere, then regenerate random numbers and write it down somewhere again. And we have to make such records of simulations depending on the required accuracy from 100 to 10,000. If we know for sure that our forecast has a normal distribution, or more exactly, the forecast error has a normal distribution, then it is enough to make 100 simulations. Then calculate the expectations from them and error variance. And using the formula for the normal distribution, calculate interval predictions. If we do not have such assumptions about the type of distribution, then it is better to make the maximum number of simulations, that is 10,000, and then calculate the quantiles of the distribution, that is the upper and lower forecasts correspond to the quantiles of the distribution with a given confidence level. After these simulations, in step 3, we calculate the mean prediction simply as the simulation mean and the error variance. And we build upper forecast based on this normal distribution, if we theoretically know that they have a normal distribution. In particular, the normal distribution exists when we predict the ARMA model. If our indicator y does not have a normal distribution, either the model error is not normal or some kind of complex system due to which some effects arises, then we evaluate these interval forecasts as distribution quantiles for the resulting sample. As I said, in this case, it is better to increase the size of the number of mutations to 10,000. Here I will give some comments. If the model was built on the logarithm, then the indicator yt plus h will be the logarithm of the original indicator. That is, this simulation forecasting needs to be done on the logarithm. And after that, you construct the average forecast and the interval forecast according to the logarithm of your indicator. You will need to take the exponent from them, and then you will get a forecast of the original indicator. Here I illustrate the differences in forecasts between the moving average model and the ARMA model if we use simulation to calculate the ARMA interval prediction, and if we use the error variance derived from moving average 14 to construct the prediction. Here is macros used in Excel to create 1000 simulations of a 2099 period forecast. Let's comment on it. You have these macros in the US inflation forecast file in your handouts. If you are going to be doing simulation forecasts in Excel, these macros you will need. So sub is the name of the macros or the name of the function. 4 is the cycle that shows us how many simulations to do, here from 1 to 100. So this macros does 1000 simulation. It rates the value n from 1 to 100. Next 10 is the end of the cycle. that is everything that is in this entry between 4 and next n, it will repeat 1000 times. Alternatively, changing the values of the variable n from 1 to 1000. Calculate is the command to update the calculation of cells in Excel, that is, generate new random numbers in Excel. In order to run the calculate command, it is mandatory to enable the following feature: formula, command, calculations options, and manually. That is, if it will stand automatically, then every time when macros command is executed, it will generate new random numbers for us. But we do not need this. It will take too long time to count and will make an error. Therefore, you have to enable the feature manually. And then we have cycle for e from 1 to 299. This is how many periods we make a forecast for, and it goes from 1 to 299 in turn. Next y is the end of the cycle. And then we have a cell to write where and to write the value. Worksheet start is the name of worksheet. Cells is an indicator of a cell. The first number corresponds to the row and the second number corresponds to the column. And this is from where to write, from which sheet, from which row, and from which column. It can be seen that a row and column here is a simulation forecast. Every time we've got a new simulation forecast. And where to write, n gets over. This is a different number of simulation. First, second, third, and so on. So end sub is the end of the macros. So here you can, in the figure, see that there is a slight difference. Simulation modeling by the ARMA model gives a wider interval than the predicted errors estimated by the moving average models by the theoretical formula. The average forecast for them are exactly the same. Well, indeed, let's say, in the absence of any calculation formulas for the ARMA model, the simulation forecasting for ARMA in Excel gives the most correct result. Therefore, this is the first simplest opportunity where you can use this ARMA model in practice. Having dealt with how to construct forecasts manually, now we finally move on to R. How to make predictions on ARMA model in RStudio. First, we estimate the parameters of ARMA model. That is, we introduce some variable. Here I have M-inflation version 2 IR4. Then we use the ARMA function, evaluate the parameters of the ARMA model using data CPI. This is the data on the price level. ARMA model parameters are 4, 1, 0. That is, this is an autoregression of order 4 on the first differences, because here my initial indicators are the logarithm of the price level. So we show that we need to plot on the first differences. And the moving average order is 0. So include constant is true. There are different things in the ARMA model. Include constant, include mean, include drift. You have to read the manual carefully. There, in some cases, if you analyze on the first differences, you need to write include constant. There, if on 0 differences, you need to write include drift or include mean. I don't remember these subtleties. Every time I look at the manual and check what I need to do. Always you can check the results as follows. If you analyze the series without drift, then it will give you a horizontal forecast. This means you forgot to include a constant here. If your initial series is not stationary, but has a such increase, then this means that drift is enabled. Of course, for a non-stationary series, there must be a forecast with a drift, because this property must somehow be extrapolated over the future, with the exception of subtleties that are specified separately. Maybe somewhere in the future we will meet these cases. Method is the method by which the parameter estimate is found. Well, there the most standard method is constant sum of squares and maximum likelihood. First, a preliminary assessment for OLS, then for the maximum likelihood. That is, here we have obtained an estimate of the parameters in this variable. So coef test is a function. We've got the coefficients of the model. Summary is the different way to get a report on this model. And here it is, in fact, the function of forecasting according to the ARMA model. This function is called forecast. In this forecast function, you enter the actual ARMA model you build and enter the forecast period h. Also, if you read the help for this function, you can enter the confidence interval that are shown to us there. By default, the confidence intervals, there are the 80% interval and 95% interval in the second one, which is indicated in the light gray. These confidence intervals can also be changed. Please see manual for this function for more details. Plot forecast IR4 is to plot our forecast variable on the chart. Here it gives us such a graph. And write the numerical values of this forecast to a file if we need it, then this is write CSV. What exactly we write down, where we write down, and here the path must be registered. And it uploads this data to you in text format. And then you can write this text format in Excel or wherever you want for your reports, building other graphs, and so on. By and large, these are all the functions that we went through on the function you then fill in automatically. But don't be happy that you don't have to learn all these calculation formulas, because any complex model requires either simulation or formulas. Well, also within the framework of our course, I will require your understanding how everything is done manually, and not just by pressing one button or one command in RStudio and simply showing the graph. Such an attitude to this course and professional education in general, when the student is simply trained to press buttons and interpret the results, will not work. A student in the modern world must be able to calculate all this manually and understand the subtleties of how it works. As soon as you move away from some stereotypes, as soon as you have to solve a non-standard problem, you should understand the underwater essence of the iceberg. how it is actually formed and why it is so. Because any deviation from the templates causes a deviation from the standard buttons and functions, and if you don't understand this, you create an error. The next part of our lecture is some comments on how to generate data on an ARMA model in RStudio. How to generate or simulate this random generator in Excel I showed you. These are the norm inverse function and RNDF function. And then you must construct a simulation forecast. But how to do it in RStudio? Here you have 3 examples. In RStudio, ARMA sim function extensively are used. ARMA with a small letter is a slightly different package than ARMA with large letters, but the function itself also works. Here you set the parameter. Here I have an example for the ARMA 1.1 model. We entered the parameter A1 autoregression, B1 moving average, and A0 constant. Next, set the TS sim variable in which you write the ARMA sim function. The number of generated data is 100. You set the function itself. Here in the list parameter, you show that the number of autoregression parameters is 1. If you need 2, 3, or more, you list them, separate by commas, A1, A2, and etc. Then the program will understand that it is necessary to generate according to the AR2 model. And we specify the required number of parameters MI. If you need to specify only the IR model, then just delete MI. Delete the comma. Specify only autoregression variables IR1, IR2 here. Without MI, this will mean that the generation takes place according to the IR2 model. SD is the standard deviation of the residuals. You must also specify it numerically. And plus A0 is a drift. According to the formula, we have ARMA sim plus drift. It is enough to write it in this way. Plot test sim. Here you have the series generated by the ARMA 1.1 model with such a standard deviation and with such coefficients. Here you go. I made a generation, launched again. He did some new generation of random numbers for you. Now let's make data generation according to ARMA 0.0 model. It is a little easier here. The same, use the ARMA sim function, leave the list variable empty so that is generate according to the model 0.0. When you need to add mean and standard deviation, you can use this mathematical property of the normal distribution. That is, here you will generate a normal standard distribution with mean of 0 and a standard deviation of 1 for one array. And in order to bring them to the mean and standard deviation, we need first multiply what you generated in the previous step by the standard deviation and then add the average value. Therefore, here you see a different formula. Generation process for ARMA 0.0 with a given mean and given standard deviation. Further, I have how to combine together 2 imitations. That is the first ARMA 1.1 imitation and the second ARMA 0.0 imitation. To combine it, here is a function in RStudio via vectors. C is a vector. It turns out just list the vector TSSIM separated by commas and add the element of the next vector TSSIM 1 to it. And so we've got the first imitation, which is on the previous chart. And here, after 100 values, the second imitation is obtained, which is made according to this ARMA 00 model. That is, here we have combining two different imitations. This is also for us in the future as a functional, these things will be needed. The last thing here is how to generate data that has a model on the first differences, but we need to get a higher level indicator. That is, here we have to register in ARMA SIM the order of the model that we are generating. That is not only the coefficients ARMA, we will also have to write the order. Here we must indicate that we have 1, 1, 1, where the second one is we show that we are building an ARMA model on the first differences. And we need a higher level indicator. Well, further as the initial value of this indicator, the program takes 0 by default. So in order to get our series that we want, we must add some initial values P0. That is, here we generate the new value of the TSSIM2 as a combining of factor from the initial value. That is the last historical value that we have, or here you can add some actual historical values that you had. That is a whole vector of previous values and the last historical value or initial value plus what it generated for you with TSSIM2 earlier. And so we build plot TSSIM2 type L. So what sometimes it doesn't build a line for us, so type L, so that it doesn't build points but a line on the chart. Therefore type L. Here I have added to the plot, and now he gives us these accumulated values of indicator. That is not the first difference on which we build the model, but the initial indicators themselves, the generation of the initial indicators on which we build the model. These functions, of course, are easily to do in Excel. But by and large, in RStudio, you also need to learn how to program all these, because you will understand that when you do more complex things, it will be very difficult to combine RStudio and Excel. Some tasks you will have to solve only in Excel. This will be needed in practice. You will understand some tasks that is easier to do them in RStudio right away, program everything there, and work with it all. Therefore, by and large, both should be mastered as tools. So now we should understand some techniques about estimation of parameters and construction simulation forecast in Excel. Here I will give you some tools for working with Excel, for evaluating parameters and constructing the simulation forecast in Excel. To evaluate the parameters of ARMA model in Excel, there is a solver function to find a solution of optimization task. Many of you knows this option. I repeat once again, we have it on the data, then to the right solver. If this function is not there, then you need to execute command file, options, advanced, go, then check box solver. That is, we turned on this function. Now estimation of the model parameters. In the Excel, in the file US inflation forecast, we have AR Excel, MI Excel, ARMA Excel sheets, where all these things are done. Here we have an example on the slide for US GDP. That is, I have data on US GDP. We consider the logarithm of US GDP, the first difference of US GDP, and here we are constructing a model that is in this column E. We enter the corresponding equations of autoregressive model with links to the parameter cell, which are still empty. Parameters A1, A0, we should have them empty. We fix these references to the parameter cells. Here they are. You see, they are here spelled out in more detail. Here are their formulas. We fix this in1 and in2 by pressing F4 buttons. And then we copy it all down. Here the target cell. In the target cell, we introduce the methods of least squares or conditional likelihood. For the least squares autoregression model, it is quite enough. Some squared differences. Array 1 and array 2. Array 1 is the original first difference by which we train the model. Array 2 is the model itself, or vice versa. It is not so important where what is the first and what is the second. So you can change array 1 and array 2. And then we execute the command solver. Target field, what we have to optimize, the target cell. Choosing what we are optimizing, we minimize this target cell because this is the least squares method. By changing the cells of the variables, changing the parameters A1, A2. The checkbox make unrestricted variables non-negative must be unchecked. Otherwise, we'll have restrictions on the coefficients that they must be generated by 0. Click Find Solution, and here we've got this solution and already is optimal solution, that is these parameters. Here the slide on the simulation forecast in Excel. We have already evaluated the model parameters in Excel and the standard deviation of the residuals. Here we have the residuals of the model. We have the first difference minus the model itself. Here we have the residuals of the model and calculate the standard deviation based on it. Here we have the standard deviation of residuals. It's sample standard deviation for the residuals of model sigma epsilon. And then to simulate the residuals, to simulate the random error of the predicted value, we extrapolate the residuals or error through the function norm inf and the expectations equal to 1. And the standard deviation that we calculated in the previous step, this is the cell E5. We entered this formula fixed to the reference to the variance. R&D will generate new data each time and copy it down. At the next step, we simply copy the model formula down, that is extrapolated. We insert the formula of the first difference here as a model plus the residuals. Here it is, step 4. So the simulation forecast of the first difference is our model plus the residuals. Here we write the model plus the residuals. The simulation forecast of the logarithm is the previous value plus its first difference. That's the formula. And the forecast of original indicator, it is always the exponent of the logarithm. and every time you press the F9 button or when you replace cells, these are all formulas, they will be recalculated. The recalculation of these formulas in the property of this simulation forecast that we are constructing. Now the subtleties with the estimation of the parameters and the construction of the simulation forecast for the ARMA and ARMA models. That is, with the ARMA and ARMA models, the problem is that we do not have error series. Here we have errors in the ARMA model, and here we have error indicator in the ARMA model. The property is that the error is the actual values minus the model value. And in Excel, we can get an estimate of the parameters of the ARMA model or the ARMA model using this property. That is, let's say we have in Excel US inflation forecast where you can see an estimate of the ARMA parameters. Here we enter the ARMA 1.1 model as the autoregression parameter. Here it is year 2 multiplied by previous values of the first difference plus the moving average parameter E1 multiply the invisible previous error. But we introduce it as error, the first difference yt minus 1 minus the model value of the first difference yt minus 1. For the previous value, we don't have a model value, we omit the starting values. It is equal to 0. But further, when copy down, we already have a model value equal to something. And then, after copying it just like the autoregression model, we calculate the residuals, enter the goal, the sum of the squares of the difference. The goal can be entered here starting from the 15th row, that is, ignoring the first lines. And in the same way, we start the search for solution and minimize our goal. This is the OLS method here. The sum of the squares of the differences is recorded. Therefore, we do not minimize. That is, in fact, using Solver in Excel allows you to very well optimize these numerical values of the parameters for estimating the moving average and ARMA model without resorting to the representations or any other things. That is, in this regard, Excel is very convenient for the autoregressive model, moving average and ARMA. With the help of the solver function, it allows you to make parameter estimation very easily, and accordingly, the simulation forecast for the ARMA and ARMA models is built in the same way as the simulation forecast for the autoregressive model. Now, when you have simulation forecast, in order to do a Monte Carlo simulation, you need to write down the value of the simulation forecast for various simulations somewhere. Therefore, it is very convenient to create a new sheet. I call it stat. Here we have forecasting periods row by row. It is an Excel file with a GDP forecast, so the years go by row, by column. This is the simulation number. The first simulation, the second simulation, the third simulation, and so on. They will be all different. We can make from 100 to 10,000 times. Only in Excel, in order to make more than 250 imitations, the file must be saved in a new version, not just XLS, but XLSX. The essence is that in the older version, the sheet is limited to 2055 columns. Here, in fact, is our logarithm of the initial series according to which we build a simulation forecast. On this stat sheet, we copy this thing with the help of macros. Here we copy the first simulation here, then we do the generation of new random numbers, and we copy the second simulation. We do a new generation of random numbers, and we write down the third simulation, and so on. As for the technical issue, I wrote it down. We enable the markers function. It can be disabled due to security issues. Here, turn on, save the file with macros support, close Excel, open saved file again. To write the macros code, do the command view macros. Such a little thing opens, enter the name of the macro and the name, press create. And we enter the macros code by analogy with the example that was earlier, where we had 2 cycles, where we did simulation modeling for the ARMA model about US inflation in the United States, and press the execute button so that this macros is calculated. To be honest, for professional work, if you want to really learn something, working with Excel is very necessary. This simple macros is needed for you too. You know where you will be working in 5-10 years, and there is quite a lot of work. Here are people in the field of economics and financing who are involved in the evaluation of investments project. There is a whole programming of complex system in Excel. So working with macros is very necessary in practice. Here I once again have a macros for simulated forecast. Now for the US GDP per capita. Everything is the same as for inflation we had. We calculate the average forecast, the average variance of the forecast error through the sample variance formula, build the upper and lower forecast based on the normal distribution of this forecast value with the parameters average forecast and error variance. And now if we have a more complex model, and for some reason the forecast error does not have a normal distribution, this is often the case in the case of more complex models, then we just have to increase the number of simulation, not use 100, but 1000 or 10,000. Upper and the lower forecast we calculating using the percentile function. The percentile gives us the quantiles of the sample distribution. We indicate the sampling distribution itself according to simulation forecast in the form of an array, and the probability is our required percentile. That is, if we want a lower forecast with a 5% error, then percentile is 0.05. If we want an upper forecast with a 5% error, then percentile is 0.95 is entered. Well, that's all. Here I showed the basic literature. In principles, according to this lecture, probably there is a forecasting formula in Psi. Everything is very complicated here, and it is difficult to read this. And I adapted these forecasting techniques to you very much. In my opinion, you will not find simpler version of the forecasting techniques in basic textbooks. Now, everything is written there, much more complicated. You will have to figure it out. Thank you for your attention. The lecture is over.